what I want to talk about are some patterns in the elements of the periodic table. Now, we're not going to go through every element, but I want to look at the first 20 elements and look at specifically some patterns in the electrons. Okay, electrons are kind of the key particle or the key part of an atom that have to do with the chemical properties of an element. Okay, so on your paper, let's write the symbols for the first 18 elements. And I want it to kind of match the periodic table. So we'll do 3 rows. Leave some space in between them because we're going to do rings. We're going to do Bohr models. Okay? So then we have beryllium. And then we're going to skip a big gap. And then boron, carbon, nitrogen, oxygen, fluorine, neon, helium is above that. And then I'm going to have to make these smaller. Magnesium. Wow, I can't think. Aluminum, silicon, phosphorus, sulfur, chlorine, argon. Sorry, I made them smaller because I'm going to have to put more rings. Yeah, follow along with me.
We're doing the first 18, right?
I want to do the Bohr models of these elements, and we're going to look at some patterns in the electrons. Okay. Yeah. I would. They're not as hard as you think. Okay. Let's start with hydrogen. We're going to assume that all of these atoms have a 0 charge. Okay. If hydrogen has a 0 charge, can you figure out how many electrons it's going to have? I have a vote for 1 electron.
Yeah.
How do we know that? Hydrogen has 1 proton, so if the charge is 0, I need 1 electron to cancel it out, right? So in my Bohr model, I'm going to put a ring, and I put 1 electron on that ring. Right?
Pretty easy.
Pretty good. Okay, let's go to helium. Helium has 2 protons, yeah? Last I checked. Which means if it's going to be a 0 charge, it has 2 electrons. Can I fit 2 electrons on the first energy level?
Yes.
Yeah, so we'll put them both there. Okay, I'll just do little dashes or little lines.
What are we doing? The 2, 8, 8, 18.
Yes, we got to follow the 2, 8, 8, 18 rule. Okay, lithium. Here's my first energy level. I need 3 electrons, yes? Right, I'm going to put 2 on the first energy level. I can't fit more electrons on the first energy level. So I need to go to the next energy level and put my electron there. Okay, if we follow this pattern, you can probably just finish it on your own.
Yeah.
Okay, how many electrons can I fit on the second energy level?
8.
8. So I can do all of these, and I think I can fit everything on 2 energy levels.
Do the first 10. Why are you only making 2 more? My bad.
Does it make sense now?
Yeah, I didn't see your other marks.
Okay.
7, 8.
Should have made these way smaller. Okay, we're just drawing the Bohr model for the first 18 atoms. Okay, this is good practice too, just for drawing Bohr models. Okay, if I go over to sodium, I know I definitely need at least two rings here. Sodium is element number 11. So I need 11 electrons. I've already got 10 here, and both these rings are full. So for sodium, I have to go to my third ring so I can fit all of my electrons. And I am not going to have space here. I'm going to do my best. I think I made it fit. I need to put my electrons in though now, right? So I could fit 2 electrons on my first energy level. I can fit 8 on the next one. Movie time over there. Magnesium takes 12, so I need 2 more, right? So 2 there. Okay, and it's the same pattern. I fill everything in, and I'm going to be, in this row, I'm adding electrons to my outer energy level. Then argon should have all 3 rings full. I think. 2, 8, 8. Gives me 18. Yeah. Okay. Gives a few more seconds to catch up if you're drawing along.
Ran out of room, sorry.
Okay. Yeah, it's tight. Okay. So, as we're finished drawing these, let's look at these. What are some patterns that you might notice in these elements that we've drawn here? Brody, you were about to say a pattern?
Oh, no.
Oh, okay. Someone else. Do we notice any patterns? Trinity?
The first row is first rings, second row is the second rings, third row is the
Ah, all the elements in a certain row have the same number of rings. Okay, so this is 1 ring, right? 2 rings, and then 3 rings. Okay, I wonder if we did potassium, if it would follow that pattern.
Should.
How many electrons would there be in a neutral potassium atom? 19, right? Because it has 19 protons, so I would need 19 electrons. Let's see what happens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I have a 2, 8, 8. To get to 19, I need another ring. How many rings did I make?
4.
Oh my gosh. Okay.
We do that like, what's the FR stand for?
Francium.
Let's do that.
We could do, yeah, skip all the way down to francium. Yeah, it would have 7 rings. Yeah. Well, what do rings represent? Energy levels. I heard several of you say it. Energy levels. So check it out. What we've noticed about our periodic table. The row that an element is on represents how many energy levels it has with its electrons. That's pretty cool. Okay, other patterns besides the rings. There's another one I'm thinking of. I'm trying to telepathically send it to your brain, see if anyone can pick it up. What other patterns do we notice with the electrons here besides the rings? Like goes up by 1 each element. Okay, good. What else? That's not what I'm thinking. I'm trying to focus on electrons. So we found a pattern with rows, that there's something in common for each row, right? The same number of rings. Everyone look at the columns. I have 1, 2, 3, 4, 5, 6, 7, 8 columns. Is there something in common for the elements that are in the same column? Okay, look up here. We're looking at the electrons. They do.
Do they all like?
The ones in the first row have on the outer rings.
There we go. That's what I'm looking for. Look at the outside ring. How many electrons are on the outermost ring here? 1, 1, 1, 1 on the outer ring. What about this outer ring? 2 and 2. 3 and 3. 4, 5, 6, 7. Do we see that? So in the columns, the outer ring has the same number of electrons. I have a different number of rings, but the outer ring matches for all of these. Okay, that matters. Now, there's a special name for electrons on the outer ring. We said it like a week ago. I'm curious if anyone remembers the special name for electrons that are on the outer ring. Starts with a V. Should we play Hangman?
Valence electrons.
Valence electrons, there we go. This is definitely going to be on the test, okay? Valence electrons. Okay, as a reminder, in case you didn't write this down, this was when we were in the other classroom, okay? Valence electrons are on the outermost ring. Outermost ring, okay? And because they're on the outermost ring, that means they have the highest energy of all the electrons in the atom, right? Because the rings represent levels of energy, okay? What do they do? Why do we care about them? They form something. Chemical bonds. Yes, they form chemical bonds. Now, we unfortunately don't have time this school year to get into all the details of how we form chemical bonds. Okay, we will talk all about that in chemistry if you decide to take that in a couple years. It's an optional class. Okay, but I'm just gonna plant that seed in your brain, hopefully, that valence electrons are important because they do this. And as chemists, we care about this because that explains a lot about how chemistry works. Okay, so they form chemical bonds. So the pattern that we have for columns is that elements in the same group, right, period group, elements in the same group have the same number of valence electrons. Haley, question, or are you good?
It was off topic.
Okay. So here's the two patterns that we noticed today. Number one, elements in the same period have the same number of hopefully it's our movie. Same number of energy levels, yes? Represented by rings. Yeah? And then the other pattern we noticed is that elements in the same group, which is a vertical column, have the same number of what? Fill in the blank.
Valence electrons.
Nailed it. Valence electrons. That's how I abbreviate valence electrons. Okay, valence electrons. And so one of the consequences of this is that elements in the same group have similar chemical properties. Okay, when we say chemical properties, what I mean is they form chemical bonds in a similar way.
You drink the coffee out of the beaker?
It's a beaker mug. Super safe. Then I know exactly how much coffee I'm drinking. I'm down to 150 milliliters. Okay. Here's another way we can represent this pattern. I'm going to draw a little periodic table outline here. Okay. We have 17, 16.
Well, you have another?
I do not. Give me 10 minutes. Thanks. Okay, so this is group number 1. This is group number 2. We skip 10 groups here. Okay. Then we have group 13, group 14, 15, 16, 17, 18. Okay. I have 1 valence electron, 2 valence electrons, 3 valence, 4, 5, 6, 7, 8. There's 1 element up here that's an exception to this pattern. Helium. How many valence electrons? 2. Now, some people might argue that helium should be here, right? 2 valence electrons. Okay, and this is and in some periodic tables, helium is over here. Okay, but the other reason why that people put helium over here is because this ring is full. Notice how the energy level is completely filled, right? Because it can hold 2 maximum. This outer ring is full. This outer ring is full. Okay, when you have a full outer ring, these elements do not form chemical bonds. So because helium has a full outer ring, it does not form chemical bonds, just like the other noble gases. And so in terms of its chemical properties, you could make a strong argument that it should be in this group because it has similar chemical properties to these elements, even though it technically doesn't have 8 valence electrons. Okay. So 8 for the noble gases except helium. Okay. Are we okay with this? Questions? Okay, I want to show you one more pattern. Let me actually pull up my slides.
It's kind of cool where you drew your.
Does it match? Oh wow, that's like a perfect match almost. I'm so good at my job. This is crazy. Okay, now I want to talk about this. I want you to talk to yourself or talk to someone near you. Answer this question. What happens to an atom if it gains or loses electrons?
It changes the charge.
Does it change mass or charge?
Charge.
The charge changes. Okay, now, if an atom becomes positively charged, did it gain more electrons or did it lose some electrons if it became positive?
The electrons are negative, so we would lost them.
If I become positively charged, that means I lost some electrons. Okay? If an atom becomes negatively charged, that means it gained extra electrons. Okay? Now, one thing I haven't told you yet is that when atoms become ions, okay, which I think is what this says, if an atom gains or loses electrons, it becomes an ion. Atoms do not gain and lose random amounts of electrons. Okay, gentlemen in the back. There's a pattern to how many electrons an atom will give away or gain. And there's a consistent pattern. So for example, if I picked nitrogen, yes, technically nitrogen could gain extra electrons or lose electrons, but most commonly it will gain 3 electrons specifically. And there's a reason for that. So particular elements will become ions of a particular charge because it's more stable that way. Okay, and the guiding principle for that is this. Okay, I'm giving you a few seconds to write this down if you want, or just keep this in your brain. This is the pattern that determines what charge is going to be most stable for a particular element if it becomes an ion. Okay, elements can become different ions of different charges, but they will usually follow this pattern. It's pretty interesting that atoms that don't have brains and can't make decisions seem to follow a pattern. It's kind of weird how the universe works. Okay? Yes, and I'm going to show you a bunch of examples. Okay. I technically shouldn't say all elements want to. This makes it seem like they're alive. Okay? A better way of saying this would be all elements are most stable when they have the same number of valence electrons as the nearest noble gas. But I don't know. We like to personify things because we're persons.
Yeah.
Okay, 10 more seconds to write that down, and then I'm going to do examples, and then we're pretty much done.
Is the worksheet big or small?
It's massive.
We have a worksheet.
Yeah.
Yeah, it's exciting, isn't it? At least he looked excited. Okay, so here's our chart, okay? We have this drawn. These are the Bohr models that we just looked at. I want to start with lithium, okay? Everyone see lithium. Which noble gas is closest to lithium? You can go forward or backwards. Helium or neon? Which one's closer? Helium is closest to lithium, right? If I go back one element, helium is right next to it. It's just they're on separate rows, so they look far away, but they're right next to each other, okay? Which means lithium is actually more stable when it has the same number of electrons as helium.
Yep.
Does lithium need to gain or lose electrons to be like helium? Lose one, yes? Okay. Which means it will be what charge? It still has 3 protons. Protons do not change. But if I lose an electron, positive 1. Okay, so lithium is actually most stable when it's a +1 charge. Yes, it can be other charges, but it's most stable when it's a +1. Okay, let's look at beryllium. Is it closer to helium or neon? Still helium. So beryllium is most stable when it's like this, which gives it this charge, yes? What about boron? Still closest to helium, so it's stable with 2 electrons. Okay. How about carbon? It could go either way. Let's count. 1, 2, 3, 4 to helium. 1, 2, 3, 4 to neon. Carbon's right in the middle. Guess what carbon does? Both, either one. You can find carbon as a +4 charge out in nature or as a -4. It does both. Kind of interesting. So we'll put plus or -4. Okay, it just depends on the situation. What about nitrogen? Nitrogen is closer to neon now, right? So that means it will be more stable when it has 10 electrons total. So nitrogen needs to gain electrons, doesn't it, to be more stable? Specifically, 3 electrons, yes? Which would give it what charge? -3. 3 whole electrons gives you a -3 charge. What about oxygen? More stable when it has the same electrons as neon. Same for fluorine, yes? -1. Which noble gas is closest to neon? That's a trick question. Neon. It is a noble gas. So guess what charge it usually is? 0. It doesn't exchange electrons. It's noble gas. It doesn't need anyone else. This is why it doesn't make chemical bonds, because it's already a noble gas. 1, 2, 3, 4, 3, 2, 1, 0. Okay? Do the third row on your own. This is closest to neon, yes? But to be like neon, we gotta lose one. You're right, same thing.
Like in electrons, it's closest to or I would say,
Ashton. Okay, if we were to go down to potassium, it'd be the same story. It would be more stable to lose an electron and be like argon, okay? Okay, now I can tell you about hydrogen. Hydrogen can gain an electron and be like helium. It does happen, but it's actually not as common. Hydrogen is actually most commonly found with having no electrons, okay? So hydrogen is most commonly a +1 ion when it's an ion, okay, which is why it fits in this group well, okay, chemically speaking. It has one valence electron and it tends to lose that valence electron just like these guys, okay? Now, just to reiterate, I'm not saying that these elements are always this charge, okay? Any element can be a 0 charge, okay? Any element can be a 0 charge. When it becomes an ion, it will generally take on the charge based on what group it's in, okay? I'm almost done, guys. Focus, okay? Any element can be a 0 charge or an ion, okay? So it will either be this charge based on this pattern or neutral by itself, okay? So just to clarify, I'm not saying it's always this charge. This is what it is when it has a charge, okay? Okay, questions? Okay, so another pattern to write down. Elements in the same group become the same charge when they become ions. Elements in the same group become the same charge when they become an ion. That's pattern number 3 for today. Okay, that's the last one. So if I were to add that onto my little chart here, maybe in a different color, +1, +2, +3, plus or minus 4, -3, -2, -1, 0. Okay, so in black I put the number of valence electrons the neutral atom has. And then in blue I put what charge it becomes when it becomes an ion. Okay, questions? We already talked about this, but I just want to communicate that this will also be on the test. I need you to know properties of metals and nonmetals. Okay, we've already learned this. I just want you to make sure it's fresh. Okay, metals are good conductors. They are malleable and they're generally shiny. Okay, nonmetals are the opposite. They're bad conductors. They are not malleable, right? They're crumbly, like rocks, and they're usually not shiny. Okay, metalloids have a combination of both categories. Okay, so metalloids like silicon is a conductor. It's shiny, looks like a metal, but it's not malleable. It's crumbly like a rock. Okay, so metalloids are a combination of both categories, so they get their own category. Okay, this will be on the test as well. All right, that's the last slides of the whole school year, at least in this class. Good job, guys.